It will be.
Yeah, so as soon as I get in here and pull that presentation up again, we'll be good to go. Of course, if I remember where I put it. There we go. So scalable malware analysis. Actually, let me double check to make sure this is even the right version of the presentation before I start presenting an old copy, you know. That doesn't seem particularly fun. Actually, I'll just flip through it real quick. Make sure that's good. Yep, okay. We should be good then. Okay, so I'm Malcolm Cutshaw. As Hannah said, I am a cybersecurity researcher. I do reverse engineering. I've done malware analysis. I've done machine learning. I've done blue teaming, red teaming, etc. I've had a nice variety in my time at INL and in college and everywhere else. So it's been a good time. I keep myself very interested. So what we're talking about today is an internal research project that I was the principal investigator of at Idaho National Laboratory, the title of which was Automated Malware Analysis via Dynamic Sandboxes. And then just to note, work was supported through the INL Directed Research and Development Project, LDRD, under DOE, Idaho Operations Center, contract, long numbers. Oh, is it doing something weird? Oh, it flipped on me. That's annoying. No, thank you very much for noting that. I don't know why it decided to switch the displays on me. Typically, it will automatically select the right one, but you know how it is. You have a presentation and suddenly everything gets backwards, and it's still flipped. See if I move it over here, will it magically? It probably will, I bet, knowing how this typically goes. Wow! Isn't that convenient? Well, I should also just be able to do, let me just see if I can just set this to mirror. Oh, let me pull that presentation up again. Okay, let's go this way. There we go. You guys don't get to see all my notes, so fantastic. Okay, looks like the dots changed for some reason, but I don't care. So malware analysis. A lot of different ways to do malware analysis. We have static analysis, of course, which is the de facto way to do it, where we take, a malware sample, a binary, an executable, and we're going to decompile it, disassemble it. We might use tools like Ghidra, IDA-Pro, Binary Ninja to get a representation that's a little bit more readable for our eyes to go through. This is typically a holistic view. This allows whoever's doing this, the researcher, the defender, to be able to get a view over everything the sample might do or might be able to do. It just happens to be a very time-intensive and a field that requires a great deal of expertise. If you're disassembling C code, you need to know how to read assembly. You need to know how to read decompilation. You need to know about data structures and a large variety of different aspects. So very holistic. We're theoretically able to capture everything about the sample as long as we can understand what's going on. It's just very labor intensive. Also, we have lost static signatures out there. There's things like Yara rules, which are very popular. We also have a variety of hashes, SHA-256, MD5. There's classes of fuzzy hashes as well that are all tied back to signatures or indicators and so on. Dynamic analysis. So as opposed to static analysis, where our goal is to look at this and say, we're going to read through this, we're going to read the code of the given executable. Dynamic analysis functions on the assumption that we are going to run the sample. Running malware, always a good idea. Very much part of the process in many cases. So in some cases, you'll pull this up in a debugger and you'll step through the program. Depending on what you're trying to achieve, you might modify different locations to get your desired behavior. We also have sandboxes, which are typically a little more automated in what their focus is. So we're going to take a sample, we're going to run it without intervention, and we're going to capture whatever it does. If it edits a file, we're going to get that particular edit. If it starts a process, we're going to get that process information and so on. As a reminder, we run these in safe environments. I will have some GitHub links later. Please do not take malware and run it on your host system. I do not want to. I take no responsibility for that. So, as a reminder, don't try this at home. So, but there are limitations. This gives us what happens, but it doesn't give us what is, what could possibly happen. This is an issue we run into a lot if the malware is able to detect, it's running in a sandbox environment. But there are some pretty major advantages when we're talking about, scalability. Let's say we want to be able to analyze a lot of samples. Let's say we want to be able to analyze a lot of samples really fast. Sandboxes can be fully automatic, and in many cases they are. We're able to do parallel analysis quite easily. All we have to do is spin up more safe environments. In that case, we're talking about virtual machines. And what we're going to get out of this is behavioral indicators. So, as I said, a process, network activity, files, etc. The good thing about those is they're a lot of cases what people want. As Reed had mentioned, that's what gets shoved in threat feeds, even if it's not necessarily always the best way to do it. They're very easy to consume. People expect them. So this is a low fruit, a low level. We're grabbing the low-hanging fruit of what a malware sample might be able to do. And it does give us things like, command and control servers. It gives a lot of point-in-time information. As I said, limitations. So sandbox detection is the big one. If a malware author says, I don't want my sample to be analyzed in that way, there's a lot of actions they can take to attempt to detect their sandbox and then just, cut the execution. Now, that's a cat and mouse game that we get to deal with. We can look at however they're doing that detection, and we can adjust those things. If they're checking the processor, then we can make sure we have a legitimate processor. If they're checking, is debugger present, we can do things against that and so on. So there's a large number of things that we can do, and there's a large number of things that they can do. There's a lot of back and forth on that. That wasn't something we dived in too much for the purposes of this, but it's just something to remember. And then we also have things like dead payloads, which comes in a lot when we're talking about historical samples. Because malware exists, not necessarily just point in time, but there's also a lot of malware that is historical. That's out there. So why do we need to scale anyway, right? There's just a couple samples out there, I'm sure. There's only 3 pieces of malware that have ever existed. No one's a bad person. They wouldn't make a lot of malware. Except that's not true, and there's an incredibly large amount of malware out there. So Malware Bazaar, which is a repository that prides itself on trying to only have malware that they are sure is actually malware, and also tries to only have what they consider to be more relevant or more time-specific. They have 300,000 files, and that's the more minimal one. Things like VX Underground, and there's a variety of other malware repositories too, has over 30 million samples. So all we need to do is find a reverse engineer that is capable of analyzing 30 million samples in like a year or two, and we'll be good to go, right? I'm sure that person exists. They don't, unfortunately. And then in addition, talking about not just historical, Malware Bazaar, that more limited repository, gets 200 samples a day. So once again, we got to find malware analysis and malware analysts that can analyze 200 samples a day, and we'll be good. Although, of course, even if you check that little chart down there, that's only the average. Or really, that's actually more the minimum, to be honest. So 700 samples some days, maybe they can feel off on the lower ones. So, of course, we wanted malware for this project, so what do? We downloaded all of Malware Bazaar samples. And that was 300,000 plus. Was actually 600,000 samples, which boiled down to a total of 465 gigabytes. So a reasonable size. Fit that in, a 1 terabyte hard drive, and then that's just the distribution. That's typically what you're going to expect. There's more exe files than there's ELF, than there is so on. So PE or exe, if you're familiar with that, is typically Windows malware. So Windows, of course, gets a lot of attention, even though it's not necessarily our most critical infrastructure, just because people like to make ransomware and similar things. So, we talk about sandboxes, right? What do we end up using for a sandbox? How many people here are familiar with Cuckoo? If I say Cuckoo and sandbox, raise your hand if you know what that is. Okay. So that at the time we started this project was a repository that hadn't been touched since 2016. So it was basically a dead repository at the time we started this project. They recently released a Python 3 fork, which honestly wasn't applicable at the time. We were what, a year and change into this project. But thankfully, somebody had decided that they didn't like the fact that Cuckoo was, not moving anymore and was read-only, so they made Cape. Cape was at its inception a couple of different things. One of the things it is primarily is essentially a Python 3 fork of Cuckoo. So it is a sandbox environment. It uses KVM QEMU. It has different options, but that's one of the ones it supports. Lots of letters, lots of acronyms in here. What that boils down to is that is our virtualization backend. If you don't know what a virtual machine is, it's basically a fake system that we're able to run in a more controlled environment. We run it underneath a different operating system, and we're able to control certain things so it doesn't completely delete our system or ransom everything on our host and so on. Some important things to note about KVM and specifically QEMU is that we can get architecture emulation. What that means is if we want to be able to emulate an embedded system, we have a much better shot of doing that with something like QEMU than we do with a lot of other virtualization backends. So if we want to emulate an ARM chip, if we want to emulate PowerPC, a lot of those processor emulators are already built. Although of course, support will vary. Experience will vary. And then the source code for that virtualization backend is out there. It's open source. You can go and edit the source code, and many people have doing things like KVM-I for KVM introspection and a variety of other tools. CAPE is, as I said, open source as well as KVM QEMU. So it's out there. Once again, pull down and run malware samples at your own risk. Give you an idea of some of the things is it provides this nice, beautiful web interface, because that's what we've learned to expect out of sandboxes, right? We run a sample, it gives us some pretty indicators of whether it's bad or what it's doing. In this case, I think we just have Windows API calls. And this one we have some signatures. I believe these are YAR, and they run off a couple of different things that are produced, memory, etc. So this is our expectation of what we get out of sandboxes, is a dashboard that tells us, is this sample bad, is this sample good, what does it do? That is great for that purpose. It meets that purpose admirably, but it doesn't really scale, right? If you have to look at every single report in the dashboard, and that's how you make your determinations, then you're still doing a lot of manual analysis, even if it is being produced. It does, however, provide a JSON report that we can easily convert to sticks. Rita talked a lot about sticks, structured threat information expression, which is a structured threat language standard. It is graph-based, which is valuable for a couple reasons we'll get into, and it can be represented as JSON. There is, of course, sticks links for us to go to as well. So we can convert this to sticks. We can make it a lot more interoperable. We can make it a lot more shareable. We also get the chance to prune and take only the content we want out of these reports, as opposed to just taking everything, which is important for a reason I'll get to here in a little bit. So sticks, represented in JSON. Not sure if that's probably not too readable. So I'll keep this one short. It's JSON code. There's a large variety of properties we get off our converted CAPE report. Things like IP addresses, network traffic, etc. Not sure if it's quite readable up there, unfortunately, but you can see some source ports, destination ports, protocols. Just in this case, you're just looking at DNS traffic. But the point to make here is that we're both getting a large variety of nodes. Each of those behaviors becomes a single node. We can also further enrich it and add things like attack patterns in. So trying to tie back to things developed by Meyer to generalize and group threat, which is of course important when we start talking about scale. We also get something very valuable as well when we start talking about graph. So what you're going to see up there is that single green node at the very top, and then of course at the bottom as well, that's a malware object. Each of those little blue objects off it are IP addresses. So we have a piece of malware, and it's talking to 8 IP addresses. Each of those becomes a single node connected by an edge. However, Sticks allows us to use what's called UUIDv5. Not going to get into that too much. All it basically boils down to is that the identifier is deterministic. So whatever the content in that object is, if it's an IP address, that gets hashed and it's used to generate that identifier. What that lets us do is it means any instance where we have 2 objects, 2 behaviors, whether they're an IP address, whether they're a domain name, whether they're a file, whether they're a process, that are exactly similar, exactly the same, they will result in one identifier, which when we start to take all this and shove it in a graph database, those will all start to merge. So instead of ending up with, a very large number of disparate reports, we're ending up with a very large number of reports that start to get these connection points, like you can see in the bottom image, where we now have 2 samples, and we can see a shared overlap of 2 IP addresses. So everything starts to connect. As long as they're if they're contacting the same IPs, that will be represented. So we start to get groupings that make it very easy to tell whether, are these 2 bottom runs related? Well, they have 2 shared IP addresses. We'd have to look at whatever those IPs are to see whether they're truly shared or not. Maybe they're just talking to, ismyinternetup.com or similar. But either way, that means they're using some similar techniques. Now those were a very trimmed down example. This is a little bit more full example. Trying to give you an idea of what we're talking about when we say scale. This is still a very small example, I assure you. So a lot of different kinds of object types in this case, and you can see that same sort of connection we're getting is not just a single object that's spread out. So in this case, those purple nodes, directories, attack patterns, etc., even our enriched content. Yeah?
You mentioned that the object gets hashed.
Yes. So in this case, when we're talking about hashing, the purpose is to generate a unique identifier. So essentially the hash becomes the ID of that object. That ID is used for the purposes of the database to define links. So in any instance where we say we have that directory object, if we took these 2 bundles individually, they would both have that object. But once we put them into the same spot, once we put them into the same graph database, those identifiers are duplicates. So they just become, instead of being two different nodes, they become 1 node, and because it's the same ID, any references to that become, they basically reference the same node now. So in any instances where we have duplicate data that we are hashing, all that duplicate data automatically gets deduplicated, which is extremely important. Does that answer your question?
I think so. It sounds kind of dual purpose. So it does
Yes.
the matching and the mechanism for creating that matching relationship.
That's about correct. So essentially we get the matching for free. We don't have to spend any effort doing the actual matching. It just so happens that because we're using a deterministic identifier, we get those matches for free. We do no work whatsoever, which for the sake of scalability is incredibly important, because if we have to search every single report for a particular object, talk about big O, our time complexity will typically get extremely large. In this case, we don't have that. We have a big O of 1.
You're doing it up front, so you only have to do it once.
Yes.
Traditional, query.
Yes, and depending on what you're doing, there's different ways to optimize that process. There's indexes that exist. Depending on what you're searching on, graph databases thankfully have gotten very good at traversals, so a lot of those queries are still optimized. But in this case, we're doing it in a way that it is essentially a free comparison we get.
Cool.
Yeah.
Do you find that adversaries or malware writers are trying to counter this analytic technique? I can imagine I put in random addresses, my peers, my colleagues also do that in their malware, so you get these various connections that kind of complicate or overwhelm the signal that you're looking for.
I mean, that's certainly part of the case. That's something we actually see quite a bit. Thankfully, in this case, if we're dealing with connections, then it doesn't necessarily matter unless they're using the same address, right? So if you generate 1,000 random addresses, but one's only your real one, well, those random ones are going to be different every single time. Ideally, your real connection is. So that will definitely generate a lot more data. It means more to sift through. But we have had a lot of success with managing quite a bit of data. Let's see here. So these are the initial CAPE reports before we even do conversion. This is for 67,433 samples. So this was our second wave going through all these. This is JSON data, and it comes up to 1.5 terabytes. So this is before conversion. Our JSON, our text is 1.5 terabytes of data. So pretty substantial before we even start the process. But we were able to convert it. And this is, we start talking about scale there's a lot of different objects that are going to be generated. If you throw in a lot of noise, if your malware is very noisy, it generates a lot of behaviors, that is something we were able to deal with. Something you'll notice, and this is just to break down the objects, but if you look at the file, the deduplicated total, if I get my roughly 700,000 file objects. The reason why is because we had ransomware that encrypted most of the file system. So every single time it encrypts the file system, we get all those file objects. But if we only have every object captured once, those are still duplicated down until we get essentially one file system plus any random files it might generate, temp files, etc. So yes, there is a lot of noise. Some of these bundles get, as I said, some of those were very small. Some of these have, I'd have to go back and look, millions of nodes attached to them. They can get extremely large. Thankfully, we are able to manage it. I've not encountered any bundle that generated so much noise that we were unable to do anything with it. Now, processing times will vary, of course. It might slow us down, but generally parsing JSON data is still very efficient. We haven't had any severe issues. If they DOS the VM, for example, well, that'll probably DOS the host system they were trying to infect anyway. So kind of a trade-off for us, a trade-off for them. But what we ended up with is some pretty large totals. So if you notice, there's definitely some things we got more than others. Files, for example, as I mentioned, processes, network traffic, and then we do have some OS-specific things like registry keys, etc. Those malware objects are more or less one per indicator. And then also to mention, so I'd mentioned that deterministic identifier, right? That is the UUIDv5 identifier. UUIDv4 is random. So this is something that's built into that stick standard. So it's not something we're just doing that's weird. This is very well defined what a UUIDv5 is, what a UUIDv4 is. So if anybody else hashes it, uses the same process, they get the same identifier, which is extremely important for terms of interoperability and sharing this data, because it means that if somebody else takes the same process we do and runs it on completely different samples, we're still going to see that merging effect. Even if they were generated completely different places, across completely different time frames, we're still going to see that same effect occur. So large variety of samples, attack patterns down there at the bottom, and there's a variety of other, or there's several other types of objects that were cut off just to make space for the table. Those attack patterns are enriched, so those aren't something that's generated directly. That's like a second layer. And that's what we get as part of that graph analysis, is it makes it very easy to just tack on more data and to combine things. With a more typical JSON structure, you have to do a lot of nesting, where you're just nesting object after object after object. You can, of course, build the extra supporting for something like graph, where everything is relationship-based, and you're not doing as much nesting as you are just, building a somewhat flat graph, depending on how you look at it. Whether you're looking at that top layer, you're thinking about it in terms of traversals.
Sorry.
Yeah.
If you want to add stuff to the graph, you have to rebuild the whole graph, or can it just
No, so that's part of the advantage of doing this whole setup is you just make another reference. You know what the identifier of the object is, so you add a relationship object, and then you add whatever additional content you want. So you don't have to take the entire object, pull it out, add in additional references in this, 5-level deep nested dictionary. You just make a reference to the identifier, and you add it. So in a lot of cases, you can even reference data that doesn't really exist yet. You can have a relationship to UUIDv5 that you don't even necessarily have. As long as you know what it is, you can still create that reference, and it will link in when you start to take all this data and shove it together into a single graph soup, so to speak. So we get a lot of data, it's all interlinked, and then that's when we start to get to selectively pull out the pieces we want, look at one node, do traversals, etc. So that part of Stix and that part of the graph that Stix uses makes it very easy to enrich data and to continue to expand it out. Because for some of these things, we're not getting every object that Stix offers as a standard. There's also a lot of custom objects as well. So for example, I don't believe in this table we have geolocation, but that's something that's easy to tap onto, a domain name or an IP address for a point in time. So there's a lot of additional information that can be just added on until you get a large amount of data that is almost so large it's difficult to process but still quite doable. So scale is definitely the point in this process. So here's the little architecture diagram. As I said, this is out there. There's the only component we do not have currently open source is the guest images for the VMs, but there is some stuff to make those building at least the Linux ones quite a bit easier. We didn't even try to think about trying to put licensed Windows VMs on GitHub. Somebody would probably have an issue with that, so we didn't even try. But there is the scripts in there to make building Linux VMs substantially easier. And I will say there's a lot of tools out there for building Windows VMs for doing sandboxes analysis. Cuckoo, of course, has some stuff for that built in. And Cape actually has documentation as well, because that's our underlying tool we're using here. So building these is extremely, I won't say extremely difficult. It is a very complicated process. Thankfully, we spent a fair bit of time on the project trying to take this process and simplify it down as much as we could. So we have this whole build system in place that allows us to basically take Packer files, take scripts, and build them into a fully functioning system in layers and then let you rebuild them incrementally. So you can keep your systems up to date. You don't have to deal with I spent 40 hours this week trying to set up 4 or 5 virtual machines. So we simplified that down substantially. So out there at the top, clone down the repository, and then you're going to launch AMA deploy, which is our deploy tool set, and then that will generate a virtual machine that contains additional virtual machines. You can take that top one and image it to physical hardware, or you can, of course, keep it in that virtualized environment depending on what you're doing. For our particular setup, we did image it to physical hardware. We did keep it in a nice offline network, though, because, of course, even though we have protections in place, we need layered security, and we have a private research network specifically for this project, so nothing could ever possibly go wrong. So. And then on the other side there, that's where we start using that Cape to Sticks tool, which is going to generate the sticks report, and then from there we're able to send it to a graph database, that node right there. And you can do queries to that, as well as just querying the reports directly. So you have each intermediary step. If you want to go back and look at the Cape report, feel free to. It's just 67,001.5 terabytes, so keep that in mind. A little bit more on that deployment process. We get to, as I said, we are put a lot of effort into creating this back-end image process. So this is set up in layers. Everything's built in kind of a, it's using what's called QCOW2, which is this virtualization image format, but it is layer-based. And then we essentially embed it in that virtual machine, the top level one, which is Cape, so you can image it or you can keep it nested. Nested virtualization is a very interesting technique, and you do lose some performance, but the fact that it's possible to make a system and a system and a system and a system is still extremely useful. So Cape to Sticks, as I said, is already out there. It's already been open sourced. We will soon have a repository called K26 Data that will contain those 67,000 sticks reports. We have to go through a little bit of a process to get those out there. It is, I think, about 2 gigs compressed. 2 gigs extremely compressed, which I think comes out to like, what, 27 gigs of uncompressed data. We probably won't be able to get the Cape reports out there ever because it's simply too much data, and GitHub, which is our current place for exporting these data sets, is not too friendly to us trying to make a 1.5 terabyte repository, unfortunately. But those data sets will be out there for you to view. They do work fine in STIG. I've already verified that. If you hit one that doesn't work, let me know, and we can probably try to figure something out. So give it a week or two, and there's a large variety of data that you can play with without even getting into trying to set up this entire framework. So I'll just open it up for questions now. That particular repository, that's been up there for, Will, do you remember when we got that one up there? It's been a couple months now. Yeah, so we had the SD, we had the SDR way back. We only open sourced it, I think, 6 months ago, and then we've been doing active development on that for it. So. Oh, I'd have to look. We haven't got. I don't think we've got an extremely large amount of collaboration yet. But to be fair, we're still, we're still in a lot of presentations. We're still doing the circuit. So there's a couple other. Yeah, and that's the opportunity of doing these presentations like this is, if you guys want to go out there and use it, you know, be safe. Please make sure you're doing things right, but if you're able to do so, please do use it. Please do create issues if you find bugs. Please do create comments and, you know, give us some more feedback for pushing this forward. So, got a couple of the presentations lined up. There'll be a paper out there eventually too, to kind of release this all in the clear. Yeah.
So the kind of to summarize the difference, I guess, between so CAPE is like a full cuckoo report.
Yes.
Tons of things that happen.
Yes. A large variety of things that are unfortunately not terribly useful. For example, metadata about how long one module took 0.02 seconds to run. So they are useful for the purposes of debugging. They are useful, you know, they have an application. It's just not doing scalable threat analysis.
And then the sticks data is the stuff that you pared down or care more about.
Yes.
And I feel like, how do you get there?
Sure.
Sorry.
Yeah, no, and that's, it boils down to there's a script to do that process that converts one format to another. We spend a lot of time going back and forth between the stick standard, going back and forth between the report, and ensuring that we are able to make, you know, what data are we able to take, what data is the most important to us, and doing that conversion process from one to the other. And then further enriching and so on, because that CAPE report, as I might have alluded to, is a giant nested dictionary that is, you know, a very large depth. Not all of it's applicable to us. If we had wanted to take everything in there, we might have been able to process it, but some of those things are so unique, like the system, Windows API calls, it showed back here, that we honestly might have gotten so many unique nodes, we might have had trouble processing it. So while that stuff is still there to be taken, and if you would like to go to the GitHub, clone it down, and do that conversion process, you're welcome to do so. And I mean, we'll accept your pull request as long as it's decent. It just might be too much data to handle. The question is, what do we want to do with this?
Another question I had is like, how do you handle kind of dimension time as, you know, relationship between samples with respect to
Sure.
I think this is always kind of an interesting challenge with graphics.
So that's a visualization question that is still something that needs to be figured out. Sticks does do some things to help us along that way. For example, those date timestamps are not included as part of the data that's hashed, so we don't end up with, you know, every single node is unique. So there are some things that are already figured out. You can just do a straight traversal and then sort them by those timestamps. Visualization, of course, is ever an ongoing problem, and typically it needs to be at least tuned for whatever scale you're looking at. For example, you know, if I give you that graph, it's readable here, but if I add a couple 3 million nodes, you can't see anything anymore. So the dates are there. It's fairly easy to sort it. It's fairly easy to, you know, export as a table, export to JSON, CSV, whatever data format you want to be able to start looking in time. A lot of these things are time-stamped by when things were run, so you're able to look at it in that fashion. There's definitely a lot of correlation that can still be done for, you know, when was this sample submitted to X number of external sources to be able to try to get a tree that way. Because when we start getting some of these clustering, you might see, you know, we have cluster A, we have cluster B, and maybe C only connects to B and so on. So you do get that chaining where a sample has evolved, most of its behaviors have changed, but a couple are still the same, and so on and so on. Does that answer your question?
Yeah, it does.
Yeah?
On the sticks side, did you embed any binaries in sticks?
So is it possible? It's definitely possible to do that. We did not do that. Probably for more than one reason. If we embed malware in sticks, people might have issues with that, specifically GitHub to start, but depending on how you're doing scanning, if you embed binaries, I mean, there's ways to encode them, they won't be detected. But it's a little risky, typically for antivirus and EDR. Yep.
How did you kind of pare it down? How did you filter down to 67,000?
So that honestly, what that boiled down to is we basically took the file types we were most interested in, and we ran all of those files. So that is the entire, I'd have to go back and look at the groupings for what file types that is, but that is a couple different files as determined by, just the file magic, and we ran all of them. And that process took about 2 weeks to run those 67,000. We had done a previous test wave that had done 20,000 samples, I think, in about 2 days. So our second wave was a little bit slower because we didn't try to do some of the same performance stuff. But this only executed with, what, 10, 15 VMs? So this is, we probably could have scaled up another 15 VMs, another 25 VMs just on our one host. You can spin up hundreds, you can spin up thousands of VMs. It is very doable to process all of Malware Bazaar, even a couple or 2 magnitude higher, as long as you can scale up compute.
This could be a whole other discussion, but I'm curious too, and kind of how you customize your execution environments, and then have you considered bare metal?
Bare metal's always on the table. There is tools out there to do it. There's additional concerns with that as well. We start talking about boot kits. There's a lot of things that have to be looked into, unfortunately. Virtualization does provide an additional level of safety. When somebody, tries to write SPI, it's not going to go well for them because it's either a virtualized component, but it shouldn't reach back to physical hardware. So fog is out there. That is a tool I know I definitely came across. It just has some additional complexities, and it's going to be a slower process, but it does have the advantage of having truly physical hardware. So if a piece of malware is using that to detect it's in a sandbox, you're in a much better place. QEMU, KVM do have a fairly good process for CPU architectures, etc. It's really the sort of thing I think you definitely want to investigate when you start running into issues where you cannot get samples to run. So it's the sort of thing I would look at when you start getting a certain percentage of failure, and those samples are important to you and you need to know what they do. That's when you start looking at physical hardware. And I believe there's a second component to your question as well I missed.
Oh, yeah, just the preparation of the VMs and also like which versions of OSs you use, and I imagine things get more annoying to configure in a fertile way for malware execution as you get into more modern operating systems. I can't imagine Windows 11
Yeah, and it really depends too. There's a couple different techniques we use. So we started from the well-known standard for all the Windows VMs, VMcloak. Needed some fixing to get it to work properly and to get all of its features back online because it hasn't been truly maintained. It does everything from installing a large variety of different Office software, Adobe, tools that malware might expect to run and that we need if we want to run a Word doc, etc. To helping us cleanse any guest image tools, anything that might have gotten missed as part of our deployment process. So we started with what's out there with some fixing, and then we kind of moved past it a little bit, just adding additional things, deleting any additional traces we were aware of, and then just making sure disk, processor, etc. all were reasonable to the point we didn't think malware would look and be like, okay, I see 1 gigabyte of RAM, it's probably a VM or something. So we did our best with the provisioning there. There's definitely further we could have gone, but the guest VMs were not really, they weren't truly our focus. They are, every component of this could be its own project in some ways. The cool part is trying to unify all these together into a single process. Any additional questions?
Out of the data that you have out there, what do you think is the most interesting observables to help you with identification?
So there's a couple ones. There's a lot of objects, and this is kind of the trade-off you get with trying to do that deduplication. The really simple objects like an IP address, if it's that IP address, it will deduplicate perfectly, right? When we start talking about processes, if we embed additional information like environmental variables, the full command line, those are a little bit more unique. So in terms of verbosity, I would honestly say things like the process, that has the full memory space it's using and everything else surrounding that, the command line. It honestly makes it pretty easy to tell, and we do have some scripts out there for duplicate runs where we can say, is it using a random string here or is this a static string? We start talking like indicators. So processes, everything that's enriched like attack patterns are very nice for being able to do grouping. Beyond that, mutexes, register keys, of course, Windows only. Mutexes, I believe, are cross-platform. And then all the other indicators are smaller, less verbose, but you get better matching on them. And still, say again? How would you use a mutex? So it depends, because all a mutex is like a lock, right? So if a malware is setting a static lock because it wants to say, I only want one instance of my malware to run, which sometimes you'll get that, you see it in conjunction with things like scheduled tasks that run every single minute. If they set up a task that runs once a minute, they don't want to spawn thousands and thousands of instances of their malware because it will bring the system down, and they don't want that. It might interrupt the ransomware process, it might cause them a bad day, or it just might be too loud. So all they're using for that mutex is to say, essentially to the other processes, I'm here, don't make another. So if they're using a static lock for that, then we can detect that too. It really depends. In other cases, you're going to see mutexes that are just related to things like processes. There's a lot of work to be done that's secondary level analysis. Like an example, if PowerShell always does locks in a certain location, then no matter what they do to obfuscate it, at the process level, we're seeing that secondary indicator of this process is running. It's the same thing we saw with like ransomware, for example. It's really easy to tell if a sample is ransomware because it reads hundreds of thousands of files and then writes to them and so on. So we get a lot of these secondary behaviors where we're honestly able to detect a process quite a few different ways, even if it's obfuscating itself, just because of the behaviors. So quite a bit of data. Definitely didn't get through. There's as I said, there's an entire project you could probably do just with that 67,000 pieces of data. We didn't even try to get into machine learning, but that's another approach as well. The hope of part of this project was that giant graph, and that's split up into individual bundles, but it can be made into one graph, might be a good place to start a graph neural network for doing malware behavior analysis. So a lot there, a lot more to do. Okay, any other questions, or we'll leave it there. So back to that question slide, in case people didn't catch it. Yep. Did you have a question? Sorry.
No,
No.
preparing to class.
I've got one more question for you.
Yeah.
You're using the hashes as the index in your engine.
For some of them, yes. That table has the breakdown, but for a lot of the ones it seems applicable, yes.
I mean, that way you don't have to differentiate on the type of entity.
Yes.
Uniform, universal ID.
Yeah, we have a and we get that universal ID. I believe in sticks there are other type specific, but you can just extract the UID portion from that.
So presumably it's got, what, 64 digits?
Oh gosh, I gotta remember. It's whatever the UID v5 standard is. I don't remember off the top of my head, but I remember looking at it because I was concerned about collisions. I wanted to be cognizant of what the risk of collision was. And it seemed, I don't remember exactly the bit count. I think it might have been more than 64 though. It might have been a full SHA 256.
Okay, because then the other question is, now you're dealing with you're saying, okay, I've got an array that, is that much of a hash. I'm just curious how you deal with that sparsity of data. Are you doing a boom filter or something like that?
So it kind of depends under the hood for which angle we're attacking it from. A lot of cases you'll get similar to like a hash map for those deterministic identifiers. So that makes it look pretty fast. A lot of those are if we're doing the graph database versus doing it, we're writing our own code. It's going to be a different approach, honestly. Hash maps are though I think the de facto for most indexing methods for what we're using. Okay, well I'll let you folks go then.